Hello, welcome to the summary session of the Computational Complexity course. And so, what we'll be doing today is we'll see a quick summary of all the complexity classes that we have seen. Maybe try to see a few examples and build the whole landscape from scratch. And then that will be the first part of the session, and the second part would be that we'll just see some questions on some complexity classes. We may not have time to go over all of them, but yeah, let's see what we can do. Okay, yeah. So whenever we talk about a class, the first thing is that what is the model of computation. Okay, so throughout the course there are majorly two models that we saw. One was the Turing machine model and the other was the circuit model, and we saw that they are equivalent in the sense that the languages that can be computed by a Turing machine can also be computed by the circuit family. So these are equivalent in that sense. Okay, and what are the kinds of problems that we were interested in? So the simplest kind of problems that are interesting to us are what are called decision problems. That is, given an input, check whether some property about it is true or not. So these are yes no type answers, and these are the simplest computational tasks in some sense that we can imagine asking, because it's just one bit of answer. Okay, the other kinds of problems that we saw were counting problems. Then we also saw optimization problems, okay, which are naturally harder than, or perceivably harder than, the decision problems. Therefore, the first thing that we would want to do is understand whether how to classify decision problems based on their complexity. And what are the resources that we saw so far? Can you recall? So how do we say
Yes, we saw the time and the
time,
space,
space,
uh, and even we saw, the circuit, the size of the circuit,
circuit size? Yeah.
and
Um,
other was the counting thing where we were doing some local
hmm,
computation, but
hmm,
the messages, the count of the the number of the messages passed
hmm.
during the session. That kind of.
Yeah, so depth is also another parameter for yeah, and you have, okay, so I'll classify this differently. Then you also saw randomness.
Yes.
Yeah, so these three resources uh, that we saw, these are with respect to Turing machine. You can also define randomness for circuits. Okay, this is the RNC class and so on that we saw. But okay, these are resources in the sense that there's some axioms. So there are certain properties that if uh, a quantity satisfies, then you say that there's a mathematical way of identifying resource. So I'll not write those uh, proper, properties, but these are something called Bloom's axioms. Okay, and these are these are two properties majorly, which if defined quantity satisfies, then you say that it's a resource. So yeah, so these parameters that we saw, these are defined with respect to the circuit model, whereas the Bloom's axioms are for the Turing machines. So therefore these are resources in the Bloom's axiom sense. Okay, and these are the parameters that we saw for circuit model. Okay. Um, yeah, so I mean, apart from that, there are several other resources, but for the scope of this course, we saw these three. Okay, so Yeah.
What about the count complexity we discussed? Yeah.
So in the counting complexity also, we defined the class with respect to time, no? So we had FP, we had sharp P.
Yes, yes,
Yeah.
yes.
So
Yeah,
this
right.
P here stands for time. So polynomial
Right,
time,
I
right?
understood. Yes, yes, I understood.
Okay. So yeah. So the simplest class that we started with was the P class, or the polynomial time class, which consists of all decision problems which can be solved by a deterministic Turing machine in polynomial time. So for what are some examples of these, if you can quickly recall?
So all the problems which can be solved in the
Hmm.
polynomial time, like say the minimum spanning tree or the shortest path
Yeah.
problems.
So
Yeah.
MST, checking whether there's a cycle, um, even um, checking whether there's a perfect matching in
But
bipartite.
then these problems are not diffusion class problems.
These
Then
are not what? Sorry.
diffusion class problems. These are not
Huh.
the,
So
even though we can think of a diffusion variant of these problems
hmm.
probably,
Yeah, yeah.
but
So
these are not the diffusion class problems as such.
mm, so how do I mean by this we just mean the decision version that given a graph G, check whether there's a cycle.
Yes, yes, right.
Yeah. And here also, given a bipartite graph G, check whether it has a perfect matching. Okay. So these are some examples among many.
What about the MST? Because in the case of the MST, there would be enormously large number of the MSTs possible. So if we view this as a diffusion class problem, then what would that problem be?
So that maybe given a graph G and an integer k, check whether there is a spanning tree of weight k.
So what would be the certificate that which we can verify in the that we can decide using a Turing machine in the polynomial time? Then?
Um, oh, so if you just give the tree, that will definitely be polynomial sized in terms of the input. So I can just add up the weights and see whether
Yes,
the sum is.
yes, yeah, I
Yeah.
understood.
And
Thanks.
the minimum here is kind of like an optimization problem, because you I mean you want to find the minimum tree such that weight of t um, is less than or equal to weight of uh, for all t, weight of t star is less than equal to weight of t. This is what you want. So so what you'll do is, that okay, how do you okay, so what you could do is you sum up all the weights of the okay, so what I'm trying to say is that this is a optimization problem by nature, because you are asking for minimum spanning tree. So it is enough to consider this decision version where you give a k. So I'm just trying to justify why this is enough. So is the idea clear?
Yes, yes, it's clear to me.
So
Yeah, thanks.
can you complete this thought? So why is it enough to solve this decision version to find a solution for MST?
Yes, so if you give me a spanning tree, then I can tell you in the polynomial time
Hmm.
that whether the sum of the weights of this spanning tree is less than
Hmm.
or equals to this quantity k or not.
Hmm.
And the
But
answer would be the Boolean one.
but I want to using this. I want to find eventually. I want to find the tree with minimum. With this k that I'm giving as input may not be the minimum value.
Yes, yes.
So how do we?
So, but then this MST would be like this that so every time we will keep on. Say if the answer, if I get the answer as yes, so then I will change the value of k,
Hmm.
and I will keep on lowering the value of the
Hmm.
k
Hmm.
until I get the answer as no.
Yeah.
right?
Yeah,
So
and you
that's
can do
it.
that polynomially number of times, and eventually, yeah. In fact, what you could also do is, because MST is in P, you just run our Kruskal or Prim's algorithm. Forget about this K. Just blindly run the Prim's algorithm, and it will give you one MST T. And what you'll do is find its weight. Check if K is greater than equal to weight of T. If yes, then accept, otherwise you'll reject.
Yes.
So we can even get around that multiple calls by using this algorithm. Okay, so okay, and then the next kind of problems that we saw the uh, were the ones whose uh, solution may not be, or we don't know whether we can find the solution in polynomial time, but if you give the solution we can verify whether it is correct or not in polynomial time. So here you have a certificate which is poly-sized, and we can verify given input x and the certificate C whether accepts if and only if x is actually in the language. So yeah, so what are the examples that we saw here?
Satisfiability problem, that was an instance of NP.
We saw sat, vertex cover, click, and so on, and
Yes.
several more. And we also defined the hardest problems in NP, which we call NP complete problems, and
Yes.
all the three that we listed here are NP complete. Okay, and this is one major open question, whether, so whichever are open, I'll just draw them in red. So we don't know whether P is equal to NP, or whether they are strictly whether P is strictly a subset of NP, but all we know is P is contained in NP. Then yeah, what are the other classes here? So we also saw sigma 2, which is given Oracle access to SAT, what are all the problems that we can uh, solve in polynomial time with Oracle access to SAT. Then yeah, we can keep on defining it this way. What if we give access to a sigma 2 language, then what questions become solvable?
But
So
then the meaning of sigma 2 used to be something else, and it used to be like there exists something and such that for all y, and then the verifier results into the true value. So, but
yeah.
then, so how is that equivalent to having the Oracle access of the set?
So this is I think you did you do this in the class, that sigma 2 is same as NP to the NP, and pi
No,
2
I
is
don't remember. I don't remember.
okay.
So I remember that sigma 2 used to be like where exist quantifier comes first, and then
Yes.
for all quantifier, that's
Yeah. So sigma k in general. Okay, let's just write sigma 2. So sigma 2 is there exists x, or let's say there exists y1 for all y2. There is a decider, polynomial time decider, accepts if and only if x is in the language. Okay, this is how we defined it. Equivalent notion of that is if I give you access to SAT, or let's say NP, okay, then what are the problems that can be solved in NP? And so the hierarchy basically looks like this. So you have P here, then you have NP, and then you have co-NP. Then you have sigma 2, which is equal to NP to the NP, then NP to the NP to the NP, and so on. Here you have co-NP to the NP. It does not matter, okay, whether you write NP here or co-NP here, because Oracle is just gives you one bit, right? So if
yes.
you can just flip it. Yeah. So you can keep on defining this hierarchy. So this corresponds to sigma 3, and this is pi 3, pi 2, and now you have their intersections. So NP intersection co-NP. Okay, this is generally called delta, but okay, I'll not. Yeah, you can talk about this intersection. So I'll not get into this. And we don't know whether this delta 1 is equal to p. That is another big question. Okay, so why are these equivalent? So in some sense, what's really happening is this NP we know is corresponds to their exist quantifier, right? You
Yes.
can think of this as NP to the P. Okay, so there exists y such that the verifier accepts. This is the definition of NP, right? Now what happens is you have given access to this NP oracle. That means so why is this not a there exist? Because this NP is as powerful as a co-NP oracle as well.
Yes.
So that is in some sense where this for all comes from. Okay.
That is not well understood actually. So NP part I could understand that there exists something, but
Hmm.
then NP and having the oracle access of NP, how would it mean that for all y2? That is not
Hmm.
understandable.
Okay. So, okay. So basically, what this means is, okay. So although this is NP, but it's in the oracle, right? So you can ask me any queries of the form co-NP as well
True, true.
by flipping it. So yeah, so this is basically there exists y1, there exists y2, such that there is some verifier for that, and you also need to cater to the kind of oracle queries where you have co-NP because of the flipping.
True, true. Yeah, I understood.
So although this is subsumed, it is this part because of which the co-NP type of queries, because of which this for all comes in. And now why is this same as there exists for all there exists? Because you have there exist here given access to a language in NP to the NP, but again you could have queries of the form co-NP to the NP. So
So like in the next level for the sigma 3 NP there exists, and for another NP it's for all, and then for another NP then you would be considering it as say there exist only, and why
because
not for all then?
because you are actually considering both. So it is there exist. Okay, now for NP to the NP it could be for all. Okay, let's do it. Okay, so there exist. Basically you're going over all possible or all possibilities. Okay, whether this is co-NP or not is independent from this is co-NP or not. Or it could be there exist for all like you said. Okay,
Yes.
now this is also subsumed, or it could be of the form there exist for all there exist.
Why there exist, and it, I mean after
Because
subsumption it should be for all.
so this is NP to the co-NP to the NP, right? It is also allowed to have NP queries or co-NP queries.
Can't be writing it as NP and then raised to the power say co-NP and raised to the co-NP.
Yeah, so that is what this is, no? There exists for all, but this will get
Yes.
subsumed. And it could also be the other case that there exists for all, but then that will just become there exists for all.
Yes. So if we take end of this, there exists for all, with there exists for all, there exists, the result would be there exists for all. Not there exists for all, there exists. But then in sigma 3, we used to view it like say, there exists for all and then there exists.
So what if only this machine is co-NP, but this could still be NP type queries.
This could be co-NP as well.
This could be co-NP as well. So we are going to take all possible cases.
Yes, okay. Well,
That is fine, no? So that case is also there, but it only gives you there exists for all. But this could also be there, that this oracle is actually asking there exists type queries.
Yes.
Although this is not, I mean, this is a very shortcut type of argument, but of course there is a proof for this. Okay, I'm not sure if it has, but yeah, I mean, this might be there in Aurora Barak. So let's just check it out. Okay, so I mean, okay, we didn't formally do all of that. This is just
Yes.
intuitive.
Yes. Yes.
Okay, so okay, and so I'll not write all of it, but we know that uh, this is contained in the polynomial hierarchy. Okay, and so these are all the classes. So far all the classes that we defined are with respect to time. Uh, okay, and you also have exp, and then you also have nexp. Okay, all these variants, but we'll just stop here. And then the other kind of resource that you have is what is called the space. Okay, so I'll use maybe a different color to
And what's the relation between this entire PS thing and then EXP?
entire ph and exp.
EXP.
Hmm.
What is the
ph
relation?
is
Do
contained
we have
in
any relation?
ph is contained in exp,
Okay.
because you can just simulate so you can simulate, for example, let's say sigma 2. mm, hmm. Okay, I'll get there. Okay, I'll get there in a minute when we define one more class. Okay, so then with respect to space, what are the classes we saw? We saw non-deterministic
We
log.
saw NL,
Huh.
NL, and then L. L
L.
was there inside N. Yeah.
Yes, and we don't talk about logarithmic time because your input is of size n, so you'll need at least n amount of time to at least read the input. So there's no other way that you can take lesser time than the size of input itself, so it doesn't make sense to talk about logarithmic time. Okay, so yeah.
And related to this statement, then why do we have algorithms having the complexity square root of the n? If we require at least n amount of the time to go through the input once,
Hmm.
then how is that possible that the execution time of some of algorithms came out to be the square root of? I mean sublinear algorithm.
Oh, so sublinear algorithms are altogether okay, are a different thing, because the model is that, so here what is our model? Okay, the model is that input is given to you on the Turing machine, and now you are uh, supposed to run on the work tape and so on. But in sublinear algorithms, what happens is the input is not typically given to you in a fixed form. Okay, so input is streaming, it is continuously changing, and you are expected to produce your answers on the way.
Okay. All
Okay,
right.
so otherwise if the input is fixed, then you can't hope to do better. But yeah, yeah, so here the input is continuously streaming to you.
Yeah. Thanks.
Okay, good. So okay, and then we can also talk about the algorithms that take polynomial amount of space. And so why is it here? Of course p space would be contained in p. It's also sorry, contains p, and it also contains np, because that would just mean that go through all possible. For example, you want to solve sat, what you could do is just go through all possible assignments one at a time and check whether the circuit evaluates to 1. So you're just using linear amount of space in that. So yeah, so therefore np is also contained in p space. Now, why is pH contained in p space? Because it's the same idea. So, no matter how many, I mean, you have some polynomially many quantifiers here, okay? Uh, or you can think of TQBF, right? So, TQBF is complete for p space.
That's true.
Yeah, and yeah, and mm, I mean, any problem in the pH can be quantified as uh, in some sense there exists for all, and so on, followed by a verifier. So you can think of uh, a pH problem as a TQBF instance.
So this pH is contained in P space, or do we know the relationship in between pH and P space, or
Yes, pH is
yes, we know.
contained. Yeah, pH is contained in p space because you can view any problem as TQBF, and this can be solved in p space because
Yes, it's okay. But so this the format of the pH looks like the formula game kind of thing.
what's that
So
mean?
formula game, like say Antakshari game kind of the thing, wherever there exists, right? Say, so it can be good as a two-player game kind of thing. So there exists like this is the move of one player, and for all this would be the move for the another player, and then they keep on playing for a very very long time.
Hmm. That is actually those are actually p space problems. pH is just the union of this whole. Okay, where did it go? Yeah, pH is just the union of this whole sigma one, pi one, and so on.
Okay, okay, fine.
Okay, so this is just union of sigma to the, yeah. Hmm.
Probably pi is not required because say pi k is already there inside sigma k plus one.
That is also correct. Yes. So you don't need both of them. Just one of them is enough. Yeah. Good. Okay. So yeah. Hmm. Hmm. And also p space is contained in AXP. Why is that? Uh,
Because if we can if the Turing machine occupies a space of the order of fn, then at the most it would be requiring say fn multiplied by 2 raised to the power fn number of the moves in the simplest form.
hmm.
So therefore the p space is there inside exp.
Yeah. So this was the configuration bounded argument that, let's say you know that your machine runs in space S. After this, it's never going to touch any cell. Then, what are all possible configurations that can happen? So, number of configurations can be, the tape head could be at any of the S positions. It could be in any of the Q states. And what is the content on the tape? It is size of alphabet. Let's say that is 2. For now, it's just a constant. I'll just call it K. Uh, yeah, K to the S. Okay, and S is a polynomial. This is some P of n. So I'll just write as P of n, P of n, and P of n. So this is bounded by exponential quantity. And why is this enough? Because if the number of configurations are more than this, then that means the machine is looping because of repeat of configurations. But that's something that cannot happen because our machine is it's a decidable language. So therefore any p space language must run in exponential time, and the same argument shows that L is contained in p.
Yes, yes.
Yeah. So hmm. Yeah, and also mm, hmm, yeah. Okay, so I think, yeah, these are the most explored space classes. So we saw classes based on time, we saw based on space, and also based on randomness. So what are these? So we saw randomized
RP,
RP,
BPP,
BPP,
ZP.
ZPP. Mhm. Hmm. And then you have co-RP and so on.
Wow.
So,
Yes.
hmm, okay. And what are the containments?
So RP was contained in NP,
RP is contained in
uh,
NP.
and we were not knowing the relationship in between the BPP
Hmm.
and NP.
Hmm. So this is
And co-RP, yeah, and co-RP was contained in, I don't remember, was contained in ONP or
hmm. By the same
ONP.
argument that RP is contained in NP, you can show that co-RP is contained in co-NP.
And the intersection of ORP and RP was in P. Again, P was there inside this
Hmm.
RP and then ORP in the intersection.
Yeah, so we have RP, co-RP, and this is ZPP. ZPP is contained in RP intersection co-RP, and you have P inside.
Yes, yes.
Okay, so we have okay, but we don't know between BPP and NP which is contained in the other. And you also know that this is Adelman's theorem, which says that BPP is contained in sigma 2.
And it's probably something that the relationship in between NN and CoN is missing here, Emerson theorems, and both are equal.
NL and co-NL, sorry, what?
Both are equal because of that Immerman's theorem, something, yeah,
Hmm.
what was the name? Wherein you prove that
Immerman
NL is equal
Selexini.
to
Yeah.
yes, yes. NL is equal to CoN.
Yeah, by showing that the um, path problem is in
Yes, yes. Path problem is NL complete, and that is also there in CoNL, I guess.
Celeb. Uh, I don't recall. Okay. I don't, okay, I don't know the spelling. I'll just call it IS theorem. Okay, and yeah, these are some of the randomized classes that we saw. Then yeah, then we also saw these circuit based classes. So I'll draw it here. So what are the classes? NC, oh sorry, AC, and then you have NC, then you also have TC and so on, where these are the threshold gates. And how did we define AC? So NC is union of NCI, I greater than equal to 0. This is union of ACI, I greater than equal to 0, where NCI is the class of all circuits, all functions that are computable by circuits with AND or negation gates, bounded fan in, and depth I, log n to the I. And the only difference between ACI is that here the fan in is bounded in NC, whereas AC has bounded fan, unbounded fan.
Yes.
Okay, and we also saw that NC0 is contained in AC0. Okay, I lost charge. Contained in AC0, which is contained in NC1, and so on. So in general, ACI is contained in NCI and NCI plus 1. We know that NC1 in particular is contained in L. Okay, but yeah, other than that, there's not much known. Okay,
Yes.
and
And you use two terms, uniform model of computation and non-uniform one.
yeah. Okay, and what are the other? Yeah, one other class that we saw was P size. Um, so
P by poly and then it was related to P size.
yeah, so we have um, P slash poly, which is same as P size. That is, by this definition, this is the set of all circuits with polynomial size, and this is the set of all languages that can be solved by deterministic polynomial time Turing machine given polynomial amount of advice. So it turned out that both these are actually equal. And
But this P slash poly comprises of the undecidable problems as well.
hmm,
And so therefore not only this P is a subset of this, probably NP would also be a subset of this, isn't it?
hmm, yeah, that is correct. Yeah. So in fact, also BPP, we also saw that BPP is contained in P slash poly. Hmm. Okay. And okay. Yes. What? So I think these are majorly the circuit-based classes that we saw. Other than this, we saw.
IP, interactive IPS is remaining.
Hmm. So if we talk about, can just yeah. So if we talk about DIP, which is what? Okay, sorry. Hmm. So if we talk about DIP, which is what we started with initially, then it turned out that it was same as NP. Then we allowed randomness in the definition to get IP, and it so happens that IP is same as P space and DIP is same as NP. Yeah, and what are the other classes? We saw some counting classes. Okay, so so what are the counting classes that we saw? FP, uh, we saw sharp P. Yeah, these are the major two. There are several other, but we will not get into that. And and now for a long time the question was, so I remember you had asked me this question. So FP and then you have sharp P. Okay. So yeah. So for a long time what we had was, we have this decision world, right? The whole this P and so on, this entire lattice here, this is the decision world um, that we have. And on this side, okay, although we are not drawing it, this is also a huge hierarchy. You can keep on defining variance and so on. So this is the counting world hierarchy. So for a long time it was not known how these two should be connected to each other, although we knew results like if okay, if fp is equal to fnp, then p is equal to np and so on. Such consequences were known, but other than that there were no connections as such. We didn't know how to compare. So what Toda's theorem does is that it connects this world with this world by saying that ph is contained in p to the sharp p, and p to the sharp p is of course contained in, I mean of course contains p. So this result by uh, Toda bridges the gap between the two worlds, which was surprising because we didn't know how to compare them. So I mean, yeah, so that's why this result is kind of important.
Yes, and I have a small query at this point that while listing all the circuit complexity classes, you start this hierarchy from P and not from NP or any other complexity class. And why so? Is this because we are only interested in knowing the circuitries and which have got a polynomial size or something else?
I didn't exactly understand the question. So are you saying why did we connect it to
P
P?
and not from NP. I mean, not from NP.
Because you want to make connections. So of course, NP contains this, but you want to give the tightest containment. So it's a stronger statement to show that it is contained in P, because then naturally it is contained in NP.
Right, right. Can you quickly give a small? I mean, I forgot the meaning of ACI, the collection of all the problems, and wherein the
That can be solved with and or negation gates, and the depth of the circuit is log n to the I, order log n to the I, and each gate has unbounded fanning.
yes, no, thanks.
Yeah, good. And just to recall, why did we introduce these classes? It was because historically it is because we want to solve the P versus NP problem, and this circuit gave us one promising approach to separate P from NP. Okay, just let me charge again. Yeah, I'll just verbally say it for now. So the circuit seemed like a promising approach for separating P from NP. Therefore, this whole area came into place, and that's how it was born. But then there are several interesting questions that are out there. So that's how we expanded the study. But the major idea was to attack this problem. And yeah, and this idea of the randomized algorithms comes from the fact that we don't know whether BPP is equal to P. So that is another big open problem. Of course, we don't know whether BPP equals NP as well. So these are three big problems, and the idea is it's kind of analogous to the P versus NP problem. That is, if I give non-determinism as a power, then is it strictly more powerful? Similarly, the similar question in the randomized world is, if I allow you to have randomized bits, then does it give you more power than the deterministic world? So those are the yeah those are the two major questions that we ask. And um,
Can you write this line in the notes because this is such an important line? You talked about two worlds. The first one is about the time, and the other one is about the randomness. Just now, because you made this important statement that since we do not know relationship in between NP and P, similarly we do not know the relationship in between PPP and P because of this.
yeah, so let me write it here. So major uh, open questions. One is randomness versus, okay, does randomness give more power? So that is our whether BPP is equal to P. And the second is, does non-determinism or guessing give more power? That is whether NP is equal to P. Okay, and the other problems are whether P is definitely contained in NP intersection co-NP, but we don't know whether this is equal. Okay.
Yes. And you also talked about the NP intermediate problems, and probably those intermediate problems were there. I mean, probably, maybe, I mean, in the intersection of NP and the co-NP, but clearly those are not belong to P.
We don't know at the moment whether they belong to P. Yeah.
Yes. So anything which you would like to say about this difference in between diffusion variant and optimization problems? I asked this question earlier also. That I mean, so whether these complexity classes P and P are relevant only for the diffusion class problems, or is this a fact that every diffusion variant can be converted into optimization and every optimization can be converted into diffusion variant? I mean, what's the situation, exact situation?
Yeah. So, yeah. So you can think of a decision variant of it, but it's not. So, yeah. So if it makes sense to talk about the decision variant, if okay. So okay. So yeah. So every optimization problem can be if you basically you want to optimize some quantity k. So what you could do is I'll call the input I. Okay. So okay. So what like we saw earlier, right? In what was the example? I think MST. In case of MST, we said that what we could do is we'll ask for k. If the answer is yes, we'll ask for k by 2 and k by 4 until eventually we find a minimum answer by the idea of binary search. So idea is that ask decision queries using binary search idea so that eventually you get the optimal answer. Okay, but why was this possible? Because we had some bound of k to start with. So for example, if I ask you for vertex cover, then you know that the maximum size of a vertex cover can only be n at most. So you have some value of k to start with, and if you start with n, you can ask for n by 2, n by 4, and so on. In logarithmic amount of steps, you will be done. So if you could solve the vertex cover decision problem in polynomial time, then you can scale it up to find the answer to optimization problem in polynomial amount of time, because you are just going to ask log n number of times the answer to the time taken for the decision.
So does this mean that these P and P complexity classes are valid for the optimization problems as well?
Hmm. Yes. So yeah, so actually that was how we came up with the uh, yeah, with the decision version idea, that you want to find optimization, but for these problems it's enough to solve the decision problem, which seems much simpler. Okay, so for every problem in NP, for all L in NP, you can actually do such uh, I mean just convert it to decision problem, and it is enough to solve the decision problem. That will directly give you a polytime answer for the optimization problem. But beyond this, there is no guarantee that if there is an optimization problem which is not in NP, for example, say NEXP. Okay, NEXP also is defined for decision problems. I can't call it NEXP, but um, yeah, but
Take example of Tower of Hanoi problem.
Tower of Hanoi. So what is the problem? You are, but that is not optimize. Okay, yeah, it is it can be thought of an optimization problem. So you have this specs, and you want to come up with a minimum number of um.
Not minimum number. I mean, we would be having the exact number of the moves required to transfer the n number of the disk from the source pillar to the destination pillar. And if n number of the disks are there, and with some constraint that we cannot place the bigger disk over the smaller one, and then to transfer n number of the disk from the source to the destination, we require 2 disk to the power n minus 1 number of the moves.
Yeah. So,
So what about the complexity class for this problem there?
hmm. So first of all, are you talking about, so if it is an optimization problem, then you want to minimize the number of steps.
No, no, that cannot be. This is not an optimization problem, I think, because we know the exact value.
Yeah, now you know that. I mean, you know for a fact that the number of um, minimum, what do you call it? I mean, moves required will be, that is the best you can do.
Yes, yes,
But I mean, let's say you don't know that fact, you are still always interested in finding the minimum number of moves.
yes, yes,
I mean, I could give you a verse algorithm, right, that does some redundant steps, redundant moves, but it's still a correct algorithm.
yes, yes,
So, so in terms of optimization problem, we want to minimize um, the number of moves. Okay, and the decision. What would be the decision version of this problem? That given the tower of Hanoi instance, is it possible to solve it in k many moves?
right,
Okay, and then we'll do the binary search from there. But yeah, like you said, in this case, the minimum number of moves itself is 2 to the n. Sorry,
yes,
yeah, 2 to the n. So yeah, and the instance, the input instance is just of size n.
right.
So yeah, so although we can do this sort of binary search, but since the k itself is so large,
Right.
yeah, it doesn't help.
So therefore, this problem is not there in NP. Uh, Probably this problem tower of Hanoi will be there in EXP, but not in NP at least.
Hmm. Yeah. So yeah, that is correct. So this is in exp, but not in n. Okay. Okay.
And
How
how
do
did
we
you find it?
prove that it's not in np? That would be hard. Okay.
But then how did you reach to this thing so quickly? That minimum number of the moves required is 2 raised to the power n, and if we are looking for the value of k, then k is related to 2 raised to the power n.
Huh.
Uh,
So hmm. So all we are saying is that if we use this particular method of doing binary search, we will not be able to solve it. But maybe there is some other cleverer way which, I mean, which could do it.
why can't we do it? Why can't we do it? I mean,
Why
what
can't we
is the
do it
what
as
is
in? Why can't we do it using this binary search method?
yes, yes.
Okay, actually, yeah. So although this number is 2 to the n, you can store it in polynomially many. You just store it in binary. That should still work, yeah.
So what's
So,
the relation in between this k and 2 raised to the power n? Because 2 raised to the power n number of the moves are possible.
hmm.
Oh, I see. Now I got this point. So this problem is not there in NP because what would be the certificate? Certificate would be
The moves itself, which,
yes,
yeah.
yes, and the size of the certificate itself is exponential.
Hmm.
And for a problem to be there in NP, the size of the certificate should be polynomial.
Hmm. Huh. Also, we are not concluding that this is not in NP. We are just saying we don't know.
But this problem certainly is there in exponential in
It's
EXP.
certainly, yes, yes.
Yes, yeah. Thanks. That's clear to me. But still, what is not clear to me is that do we have some concrete? I mean, whether these complexity classes P and P are they valid and relevant and should be used only for the decision class problems? Number one, or is this possible that, or is this a fact that every optimization problem can be converted into the decision class problem? So therefore, for every optimization problem also, for the optimization problems also, we can use these complexity classes PNP and the other classes we discussed in this course.
Hmm. Okay. Okay. So, are you asking whether the this PNP classes are relevant for optimization problems?
Yes, yes.
Hmm. Yeah. So um, yeah. So that's what, for example, for yeah, for problems like vertex cover, if you want to solve optimization problem, it's enough to solve the decision problem. So in fact, um, yeah, in fact, for all the languages in NP, if you look at their optimization version, okay, I mean solving that decision instance will directly scale to their optimization versions. So take any example in NP, and um, yeah, it would directly scale to optimization.
Yes, I remember in one of the sessions you told that there are optimization problems and whose decision variant is not possible. Optimization problems are more difficult than the decision class
Hmm,
problems.
hmm, hmm. So I think that example was, yeah. So that will happen when, I mean, here you have a good bound on what the quantity could be, the optimization quantity could be. Therefore, you could do a binary search nicely. Okay, I think even if it's doubly exponential, for example, the quantity that you are looking for to optimize, I mean, there need not be a bound always, right?
Yes,
So if that happens, if the um, so if the bound that you could have on the quantity you are trying to optimize, that is your input instance, okay, I'll call it I, and let's say that size of I is n, and in terms of size of I, if the bound is say doubly exponential or worse, yeah, then there's basically no hope of um, I mean, using
yes,
the binary search thing.
yes.
Um, okay, did we see any examples of that kind? Hmm. I think one interesting example that was there, but that was not an optimization problem as such, but a counting problem. That okay, one okay. So one interesting example here is that you know that given a graph, checking whether it contains a cycle can be done in polynomial time. In fact, you can just do it in linear time. Okay, but if you look at the counting version of that, sharp cycles, then even approximating the number of cycles is hard. Hard in the sense, if you could approximate it by a factor of um, okay, I don't recall what the factor is. It's a constant factor, I guess, 2. Then that would mean that you can solve SAT in polynomial time. That is, you would have shown that NP is equal to P.
And will this counting include self loops as well or excluding the self loop?
Um, yeah, it doesn't matter. I mean, you can define your variant to have no loops.
Okay,
That,
okay.
yeah. Okay, so hmm.
Yeah.
Okay, so is there any other class that we missed? I think that is all the picture that we have. Mm, hmm.
Don't we have something like co BPP? Would it be same as BPP
Huh.
or
Yeah. So BPP is closed under complementation.
yes?
Hmm.
And I remember that you talked about one P complete problem as well. Yeah.
Hmm. Yeah. So yeah. So we then saw that the notion of a complete problem for P should involve yeah, these are P complete, should involve a measure that is smaller than P itself. It should be a coarser relation. Okay, so if we define it with respect to L or NL for that matter, then then one complexity class that I mean one problem that is complete for it is the circuit eval problem.
Uh,
and
yeah.
and there are, okay, now that you know these classes. Okay, so we saw that if you want to define the notion of completeness, it has to be something smaller than p. So you could choose NL, you could choose L, or you could choose any of these circuit classes. So there are notions of reduction with respect to NC0, NC1, and so on. So
So, yeah, I remember that in that class you draw one smaller circle inside this bigger one, and I preserved that diagram somewhere. Probably you wrote L inside this bigger circle, I guess. And just to show that whenever you are taking the reduction, it should be smaller than P and not in P. So can you write this fact also in a small box, because I would be keeping
yeah,
this in mind here.
um,
This fact that whenever we are reducing, so it should be reduction should be carried out in, I mean, through something which is smaller than the original.
then so I'll just write.
Should be smaller than B or should be smaller than E? Which one would be more appropriate?
Okay, so actually these are the languages within the same class potentially. So I should call it class because these are languages. So let's say A, B are in some complexity class C.
Yeah, yeah, that's right. And in this notation, sometimes
Hmm.
I saw the symbol M, and sometimes the symbol at the time of the reduction T. Even in yours lectures also, many times you use the term like say carb reduction, many to one reduction. I remember you used to say this N as many to one reduction. And the other thing which I saw in the original lectures, the NPTEL lectures, was during reduction as well. So, I mean, is there any difference or when to use which kind of reduction?
Hmm. So, okay, that is a very nice question. So, what are the mm, um, yeah. So, what are the kinds of reduction? So, there are many of them. One is many one, which is typically what we use. There is card reduction. There is Turing reduction. This is denoted by T. This is denoted by K. This is denoted by N. And uh, yeah. So when you say that A Turing reduces to B, that means um, you just assume the answers to B and then solve A. Okay.
Okay. Yes.
So one example would be so how do we compare which is a stronger notion of reduction? Like by stronger, okay, let it charge for a minute. Okay, so what do we mean by stronger notion? So for example, if you look at um, so we just said that you could define p completeness or p hardness with respect to L, NL, AC0, NC0, NC1 of your choice. So which is stronger? So the smaller and smaller class you take, the finer and finer uh, the reduction will be. So for example, if A uh, NC1 reduces to B, then A also NC2 reduces to B.
I could not understand this.
Um, okay, so okay, let us take example in terms of time. Let's say. um, let's say we have two problems that are, I'll not define what class they are in for now, but let's say we have two problems, and let's say a reduces to b in exponential time, then a also reduces to b in sorry, if a reduces to b in polynomial time, then it also reduces in exponential time, right?
Yes.
So similarly, if you show that a reduces to b with nc1 class, like within nc2 class,
Yes.
then it also reduces in nci class where I is greater than 2.
Right.
So
Yes.
that means the smallest class with respect to which you define the reduction will give you finer and finer,
Right.
uh,
Because the reduction requires resources, and if I can work with the lesser number of the resources, then clearly I can work with the larger number of the resources. Right.
exactly. So now similarly, uh, how do we talk about these reductions? Like, how do we know which is coarser, which is finer? Okay, so is it true that if a many one reduces to b, then is it true that a Turing reduces to b, and vice versa?
Yes.
So that will tell us that uh, which is a finer relation and which is a coarser relation. So what does Turing reduction mean? It just means that,
Course, you use this term course. I do not understand this course relation.
um, coarse as in, I mean, if m is finer than t, then t is coarser than m. Just the
Can you write this statement in the notes so that I
so
can see the spelling?
if m is finer reduction than t, then t is coarser than m. Just the opposite terminology.
Okay, okay, okay. All right.
Okay, so let's try to find this. Okay, whether this implies this or is it the other way around? And what do we mean by this? Okay, this one you recall that you say that a many one reduces to b if there is a sigma that will take an instance of a, convert it into an instance of b such that x is in a, if and only if sigma of x is in b, and sigma should be computable.
And moreover, if x is not an element of A, then also the sigma of x is not an element of
Hmm.
A. That is
Yeah,
also
that is what the other direction of.
yes, yes. And what about this A T during this implies?
Yeah, so x is in, hmm, hmm. So if so, think of b as um, oracle in some sense. That is, you can ask, you want to solve a, but you are allowed to ask queries to be as many, I mean, you'll have some p or something here. If this is a p, then that means you are allowed to make polynomially many queries to b. Using that, if you could solve a,
How can we write this thing in some language that improve so that I can remember this that
yeah.
is getting
So let's
next.
take an example. Okay. mm, okay, let's hmm. Hmm. Okay, so okay, before I take an example, let's just see one direction. Okay, so um, so if you look at this definition, what is essentially happening is that you are making queries to be.
Um, Making queries to B, but then how many times I would be querying to
Hmm.
B to get such a function and which can rephrase each and every instance of A to an instance of B.
Hmm. So here you are making only one query, right? Because it's just a one step thing that you will only ask b once, whether sigma of x is in B. If it says yes, then you will accept. If it says no, then you will reject.
Right.
So, so you already have one direction, that if A during reduces to B, then A also many one reduces to B.
Yes, because probably in the second case, I'm allowed to query to B many, many times. Okay.
Okay, but the other way around is not necessarily true.
And by the way, why do we call this as many to one? I mean, what's the meaning of the many here then? Because this is, if I'm querying to
It
be only once, then
it just means that this function sigma is a many one function. That is, several inputs to A could map to the same instance of B.
is this fine, or do we have one-to-one kind of a mapping that every instance of A can be replaced into an instance of B? Like, is this possible that multiple instances of the vertex cover, multiple instances of the click problem
Sure. So
can be
for
mapped to
example,
the same independent center?
yeah, that could happen. So, um, mm, okay. So how do we take an example? Oh, okay. Yeah. So let me just okay. Uh, so the reduction that you saw for, in fact, most reductions that you saw, SAT to vertex cover to independent set to click, all of them, although we write many one reduction, actually these are, yeah, I don't know if all of them, but at least these two are carb reductions. Okay, so here you will not find, um, here you will not find these clashes that happen in the many one reduction.
So, I mean, I do not know what this car production means. So, when do we say that A is getting reduced to B through car? What does it mean?
Yeah, so as far as I recall, it is the same as this, but I think sigma is no more many one. Let me just verify that.
Okay,
So that's why, yeah, that's why I think, yeah, all these reductions, basically what happened here is from G you just took a G complement.
right,
Yeah,
yes,
and here also from G comma n minus k you went to k. So here you will
yes,
only get one instance, but
yes, yes.
there are examples where you could end up getting the same. So we must have definitely seen such examples. But okay, let me just try to recall if okay. So how do you go from SAT to uh, okay? There was a gadget construction for vertex cover, which should also be unique. Mm, what are the other reductions that we saw? Um, yeah, but yeah, basically all the standard problems that you know that are NP complete are carb reductions, because the notion of um, NP completeness, when it was defined with respect to carb reduction. So what happened is, how I mean, what really happened is that all we had was this class, um, NP and P, and what happened is, Richard Carr in, okay, I don't recall the year, but it was 50 years ago at least. So what he saw is that these several problems here, um, yeah, several problems here were, um, okay, you definitely have a 3 sat here, yeah, but several problems reduced to, um, 3 sat or to each other, and the notion that he came up with So he put some 21 one by one. He started looking at problems in NP and reducing to 3 sat or to already reduced, already hard instances, that okay. And that the notion, so these 21 problems include the very famous vertex cover, is all these, right, click and stuff, so TSP and so on. And all of these are the reductions, the standard reductions are with respect to the notion of carb reduction.
Yes, and just now I googled it, and their answer is that in the case of the many to one reduction, this reduction can be carried out in whatever time. But if the time is polynomial, so along with this m symbol, if over this less than or equals to, if we write a p also,
Yeah, so
that is
this,
that is that is if this reduction is being carried out in the polynomial time, then it becomes a car production, and both the terms are being used interchangeably. So in the car production, this entire transformation should be carried out in the polynomial time, and in the case of the many to one reduction, there is as such no constraint of time. That is what they have written.
mm, okay, okay, then let me just try to search it once,
Yes,
okay.
yes, please do it.
Okay, I'll just use my iPad for that so that you can also see. um hmm. Yeah, that seems, yeah, I think that is consistent with what is written here. So okay, okay, so yeah, so what they're saying is also that if yeah, if you are dealing with many one reduction with polynomial, yeah, with polynomial time, then yeah, that's the carb reduction for
That's
you.
the car protection. Yes, yes, yes.
Yeah.
And if we simply write m below and do not write p, then this is many to one. And if we write p along with m, then this is car protection.
Hmm.
And this during is something else. And probably they have used one more term, cook, which I just saw when you were
Ha.
browsing. This cook reduction, that is something else, I guess, or is the same as, I don't know.
Yeah, should be so where was it?
I read it somewhere when you were scrolling it down. I read. when this car production thing was given, then there is cook term was also given. C double O
Yeah,
K.
yeah, here.
Is cook reductions here.
Yeah,
Stephen Cook.
same,
Polynomial
same.
time Turing reductions are also known as Cook reductions.
Hmm.
But then that is Cook reduction is valid for the Turing one. Oh, I see. So if you write P with M, then that becomes carp. But if you write P with T, then it becomes Cook reduction.
Hmm.
Okay, okay, yeah, yeah. But this the meaning of
Interesting.
this T thing is not that clear to me. Yeah.
Oh, okay. So, yeah. Yeah, so, um, where was, yeah. Yeah, so the, yeah, so like we said, that here you are allowed to sort of view this B as your subroutine and call it as many times as, I mean, depending on what's the parameter here, call it as many times as you want, but here you are just making one call.
So like say if I Turing reduces a click problem to the independent set,
Hmm.
then what would the meaning be? Like
If
say instead of going through the many to one reduction or the car production, if we reduces the click problem to the
huh,
independent sort
yeah,
problem
yeah, yeah.
using Turing
So
reduction.
yeah, so okay, I'll tell you one very nice example to see the difference. So let's say you have sat, you know that sat is np complete, and you know that sat complement is co np complete.
Yes.
Okay, and um, okay, one second, just yeah. So sat, many one reduces to sat complement, but is this true?
Set many one reduces to
uh,
set complement. Uh, uh, yes, I just need to put negation and I
negation.
can say yeah. So
but
many to one.
but is this true? um,
So in the case of the Turing reduction, if I know the solution of the complement of S, do I know the solution of if I know the solution of the complement of satisfiability, and what that complement of satisfiability be? Is this complement of complement of satisfiability? What would that mean? Uh, that formula is not satisfiable at all. Or if the formula is not satisfiable at all, then this will be the element of co-NP, I guess. Co-NP. That, and if I know its solution, uh,
okay, I'm sorry. Okay, uh, I think I did something. I think one of the directions is not correct. Okay, so let's go over this. Okay, so if you knew that, okay, I'll do it from scratch. Okay, I think I did something wrong. Okay, so we'll check first whether sat Turing reduces to sat complement. So what does that mean? If here you have phi is satisfiable, you want to check if phi is satisfiable, and here whether phi is not satisfiable. Okay. Uh, okay. So how will you do that? Let's say you have a subroutine which solves sat complement. Then what will our algorithm do? This is a subroutine for sat complement. We'll call it B. Now what does our algorithm for SAT do? It will check algorithm for SAT, we'll call it A. We will pass negation of phi to B. So now if it says 1, then we know that negation phi is not satisfiable. Hmm. Okay, actually you don't really need that negation, right? You just pass the phi.
so if I pass B to the B, and if p comes out to be 1, then phi is not satisfiable, right?
And if it is 0, then phi is satisfiable.
Correct.
So now we will just flip our answer. If, uh, oh, sorry. Yeah. So what will this do? It will just output a 0 or output no and output yes. That will solve that for us.
Right.
Hmm?
Right.
Okay,
Yes.
so SAT Turing reduces to SAT complement. Okay, but it is not clear whether SAT, I think I made a mistake earlier. It is not clear whether SAT Turing many one reduces to SAT complement. Why is this? Hmm, because you need a sigma which will take an instance of SAT to an instance of SAT complement such that uh, yeah, phi in SAT if and only if sigma of phi is in SAT complement.
So I just need to put a negative. Uh, I mean, this.
But I mean, you can't change this condition, right? So uh, you want a yes instance of here to correspond to a yes instance of here, and a no instance to no instance.
Yes. So
um, if we could for example do this, then with respect to our notion, our car production notion, we would have proven that SAT complement is also, or I'll just do it the other way around. Okay, I'll just replace it this way. Then if we could do this, that would mean that, okay, I really sorry. Okay, if we could do this, if we could prove a carb reduction, that would mean that SAT complement is NP hard, but um, yeah, but SAT complement is already co NP hard. Okay, that would actually mean that NP hard is same as co NP hard. Or in other words, every co-NP language here would be carb reducible to NP language here. So that would mean that NP is equal to co-NP.
yes.
If we could.
And yes, and I find it difficult to understand this Turing reduction because if problem A is getting reduced into the problem B, then the problem B is at least, so if A is getting reduced into the problem B, then the problem B is at least as hard as the problem A is. So how is that possible that I do have a solution routine for the problem B and I do not know anything about, like say if I'm reducing problem A to the problem B, then certainly I know one thing that the problem B is at least as hard as the problem A is. And so how is that possible that I know the solution routine or the subroutine to solve the problem B and I have no clue about solving the problem A?
Hmm. So, um, okay. So the I mean,
Take example of the click A problem as the click problem and the B problem as the independent set problem then.
hmm. Okay. So the idea here is that, okay, we are essentially thinking of B as a subroutine. That uh, if we could solve this, then there is a way of getting back to
Oh yes,
our
I
original
understood.
problem.
Yeah, I understood. This is a good kind of thing. I mean, if we can, if is included, right? I understood. Thanks.
Okay. So yeah. So I'll just um, conclude this discussion. So we know that uh, A Turing reduces to B does not necessarily imply that A many one reduces to B, and I think I wrote a wrong statement earlier. This should have been the other way around. I think we meant the other way. So let's go over this argument. We want to show this. Yeah, actually,
Yes.
this is what we wrote it the other way around, right? Because sigma gives us one instance of B, and we are just going to make that one query to B. And if B accepts, then we are going to accept, and if B rejects, then we are going to reject. So, although this allows us to make many queries to B, uh, we are just using it once.
Yes. And so can you write this definition here in this box also? A Turing reduces to be single line definition so that I can recall it later. Yes, yes, thanks.
Okay, and there's also one more small notion which is called parsimonious reduction. This is probably denoted by rho. It looks like P, but I think it's rho. And what does that mean? It just means that it preserves the number of solutions. That is, uh, yeah. So this makes sense when we talk about sharp P. You know that we know that sharp sat reduces to sharp vertex cover. Sharp vertex cover reduces to, and so on. Okay, most of these hold. I mean, these ones definitely hold, but a lot of reductions in NP do translate to the counting reductions. So you say that a reduction is parsimonious is if um, the number of okay, so how do we do this? F is in fp to the g. This is how we define the reductions in sharp p world, and this is parsimonious. I will write rho if the um, answer of, or I mean, so what does that mean? If the number of um, given a graph G, if the number of vertex cover of size k will be the same as uh, for that graph G, the number of, I mean, the number of independent sets in the
Yes,
reduced graph. So this
yes,
need not be always true. In these two reductions are parsimonious, but many reductions are not. Because what you could do is you could use this solution to compute a solution to F. It need not be the same as the solution of G.
yes, yes. Fine. So when I Google the complexity Jew, and then I find lot many complexity classes, and I have heard of very, I mean, just 1 or 2% of the complexity classes listed there. So I mean, why do we have, and how do people study about these complexity classes? So many complexity classes. Uh, there are many.
So, um, okay, I mean, okay, so are you asking, I mean, how do we study? that it's
Yes,
such a big zoo.
yes, yes.
Hmm. So, um, actually, it depends on what model you are working on or what problem you are specifically working on. So the way this whole zoo was built up is that, let's say I mean, somebody is working on the circuit problem, and then these other classes that you have, but maybe one specific problem that I want to solve maybe gets simpler um, if I restrict it to threshold, and so on. And so you can keep on defining classes inside, and that is how this keeps on expanding. So for example, I'll tell you um, one example that um, so there is one problem that I've mentioned, I guess, a couple of times, which is called the range avoidance problem. The definition, I mean, is not necessary right now, but when I was studying that problem, it was known that it is in sigma 2. I mean, there's a parallel hierarchy, it's called TF sigma 2, but it's very similar to this. So I'll just talk about this. And now now we know that the problem is here, okay? And what do we want to do? We want to put it as tightly as possible, right? I mean, we want to close it. uh, I mean, within this, where could it be further? Can we push it down, and so on? That is the question that we always ask. So then next it got improved to uh, ZPP to the NP. Okay, so ZPP to the NP is inside this. And now the question is, where do we push this further? So it is definitely between co NP. Okay, I'll just draw it. So this is where it was, and F sigma to P. This is also okay. Uh, so this is also something that got defined with the problem. So this class did not exist earlier, and they found that okay, this kind of a hierarchy could also be there. So this is how this new class got introduced. Then they saw that it's in ZPP to the NP, and now we want to ask, like, where is it exactly? Can we put it in FP to the NP, and so on? So I'll draw here FP to the NP. So you know that P is contained in ZPP. So by the same idea, this FP to the NP is contained in, actually this
Yes,
is also F.
yes, yes,
Okay. And now the question is, I know that my problem is here, it is also here, we don't know whether it is here. So how far can we push? There is nothing known in between these two. So what happened is, they came up with their own class by characterizing it with respect to this new problem, which is called linear ordering principle. Okay, I will not define it and so on, just if you want to see, you can check. So that's why I'm writing. It's called linear ordering principle, or LOP. And what they show is that this problem that we are interested in, range avoidance or avoid, reduces to LOP. So if you could solve LOP, you would have, in some sense, they are actually equivalent. And then you define a class which is complete for LOP. So all the problems that reduce to LOP will be put into one class. That class is what they called FS2P. Okay, so this is how the classes are born. It's not that we are actually, I mean, it's too huge to dedicate ourselves to go and study each of them. But most of this, how were they born? Because you are typically trying to close it, bit, like, see whether it's here or whether it's here. So you end up most of the time showing something in between. So some class that contains FP to the NP, which is contained in ZPP to the NP. Now we don't know whether they are equal. So these containments are mostly open, but yeah. But what I'm trying to say is that uh, I mean, it just keeps expanding. So people are different. People are looking at different problems. Now you put several restrictions on it. A new class is born. The new containments are shown. Some of them collapse, some of them are shown strict. But I mean, that's how it's an ever expanding zoo. You may not know all of it, so I also do not know most of it. But yeah, this is very recent. This is 2024 paper. So uh, it's by Corton and Pitasi.
And how common is this for the people in this area to propose new complexity classes, or is
It's
this rare?
actually more common than you can imagine because, um, I mean, you don't really need anything to define a new class, right? You define your own properties, and that's a new class for you.
Okay.
Okay.
And what yeah, please.
But yeah, the
You-
interesting thing is, yeah, once you define the class, what makes it interesting is how is it related to the entire tree, the entire lattice, the entire zoo. That would make the class interesting.
Okay.
And yeah, and just to tell you, then what happened is, once this new class is in picture, there was a new result which showed that um, MA is contained in, yeah. So this is our Merlin Arthur class. This showed that this is contained in FS2P. Yeah, I'm not sure if it's MA or I'm okay. I'm not very sure of this, but I think it was MA. Okay, so yeah, I mean that's how like people keep on adding more nodes and more edges into the zoo.
And how much, I mean, how difficult is this, or how much effort is required to progress in this complexity area? I mean, with the prerequisite I mean, topics which we have discussed in this lecture. But if I see some research paper, then I do not know what the problem they are talking about, the symbols, the notions they are using. So what else is required, I mean, apart from this system, to slightly progress and at least understand what those papers are?
Hmm. So, mm, yeah. Actually, most of the research that's, uh, I mean, so can you give an example of a, I mean, I mean,
So
is it something I
like
can?
say like if you pick any paper in this area, say computational complexity area, then the thing which I saw is that they talk about a problem, and that problem is something which is not a well-known problem and probably could be a very particular problem. And then they attack or address that problem by using the complexity classes, and which were quite unknown or unfamiliar to a person who has done just one or two courses on the computational complexity. So if someone wants to progress in this, I mean, to at least to understand the research papers in this area, so what else is required apart from, I mean, this computational complexity course? Which other courses, or which, I mean, what kind of mathematics, I mean, or what is required so that, I mean, someone should be able to understand at least the research papers,
Hmm.
elementary research papers, not the difficult, I mean to say.
Yeah, I think, yeah, I think this course covers like the maximum, like I think this almost covers the the fundamentals of the computational complex and the complexity part. And there are just, I would say, like there are just a couple of things that that were not covered, and these resources are available. So if you for example want to, okay, I'll just Mm, okay, I'll just show you one paper. Um, yeah. So what I'm trying to say is that you basically have like almost like all the fundamentals for the uh, on the area. Now there may be a couple of things that are uh, yeah, that are typically there but were not covered, which can be easily found in the book. Now for research, um, it will always be the case, like it's very often you look for a problem, there will be new terms or new theorems or new classes or even new techniques that you are not familiar with. In that case, what typically we do is that we try to so the classes can be easily learned because you know the fundamentals. These would be some extensions of it. Okay, for example, let me show you one, this yeah, this TF sigma 2 that I was talking about. um, Okay, the paper is called okay. So okay, so this paper talks about majorly about one problem. There are several other problems as well, but major focus is on one problem. Okay, so now uh, okay, if I could use it. Okay, let me try to get this into the good note so that I can highlight. Hmm. Okay. Yeah. So if you try to read the abstract of it, this is the main class, right? This is the class that you know. This is also a class that you know. This is FP with Oracle access to NP
Yes,
with
yes,
polynomial advice. Okay. And so this class is a new class that they are defining. So all these three classes are the new classes. Now understanding these classes won't take much of time because you already know the main classes. Okay, so okay, again, like I said, right, there will always be a lot more a lot more classes. Not all of them will be relevant for the problem. So so how do we yeah. Okay, so like I said, like most of the time it is an extension of something that you already know. So what is this TFNP? You know NP, and we also know FNP.
yes,
Okay,
yes,
now what is this T? T is basic. T just means that out of all possible functions, you are only looking at like let's say this is a class of all possible functions. It's FNP. Within this, we will look for only those functions that are total.
yes,
Okay, or bijections in that sense. So so this is how they define TFNP. So like I said, like it's just some property where you restrict to most of the times, and that gives you a new class. And um, yeah, so that is TFNP for us. And um, yeah, so similarly, like I'm saying that understanding the classes won't take much of the time. So for like okay, now the other thing is um, the techniques. Okay, so
yes,
so sometimes so the kind of techniques that are used in complexity theory are very I mean it's not like a very small set, it's a very diverse set. For example, you could let's say okay, sorry, we were already in the notes. Okay, I'll just add it here. Okay, so one part is that understand knowing the problem that you can yeah, and you may need to know some more classes. That is something you can do, but the more important part is the techniques that are used to solve the problem. So for example, what are the techniques that we used? So techniques could be a direct application of a theorem that you know, or it could be that it's similar, it's inspired by that theorem, but maybe the details in the argument are changing slightly. So for example, we saw this Cook-Levin reduction, that every problem in NP reduces to circuit sat. But then uh, later on, we also used that reduction several times. For example, we used it to show that uh, we used it to show that circuit eval is P complete. Okay, uh, maybe simpler P slash poly. So and P size. One of the directions uses this. You want to get from algorithm to circuit. So yeah. So here you have on one side you have a Turing machine, and you are going to convert it into a circuit. This is again where you use the Cook-Levin reduction. In this case, it's direct, but there are several cases where it may not be. You need to do some tweaking, some changes, some modification to the argument. So one technique is that it's theorem either direct or modifications. And so most of the times, some proof of theorem, the details in it gives you an insight into solving your problem. So that is something that happens very often. The other thing is, what kind of other techniques could you use? Like if you want to start from scratch, some arguments are combinatorial, and it uses tools from Fourier analysis. I mean, like I said, it's very diverse. It could be extremal, combinatorics. It could use coding theory, and I mean it's actually a very long list, and learning these techniques could take time. So um, these are topics on their own, like these are like big topics on their own. But if you are looking to solve a particular problem, it's up to you what tool you would want to I mean, what tool you want to attack with, what hammer you want to choose. So, although there are so many techniques, so some papers may use like something some techniques that are very different, and it will definitely take some time to like get the basics uh, of those techniques. But if you are looking to solve a problem, you could choose your own tool, the tool that you are comfortable with. And the other thing that people typically do is, let's say someone is working in coding theory, and so what they would typically know is like all like lot of techniques. I mean, these are like two different approaches. One is that you start with a problem and then you choose what tool you want to use to solve it. The other is you are actually working in one particular area. So someone is specializing in extremal combinatorics, someone may be specializing in coding theory, they know like the fundamentals of it. Now you could choose a different problem and see, okay, can I use my knowledge of coding theory to solve this problem? So both are like two different techniques. You choose a problem and choose the hammer, or you have the hammer and you choose the problem. So I mean, all of that leads to, that's why you have so many connections and very vast. Um, I mean, uh, knowledge, resources, and so on. Because I mean, all these things are interconnected. Um, so yeah. So to answer your question, if you choose a problem and you are reading the paper, you may need to know the techniques. So that could be, most of these techniques are like learnable from online sources. There are mostly videos or books and so on. That will take some investment. But if you are trying to solve it, you could use tools that you are comfortable with. For example, now you know circuit, uh, how to show lower bounds, how to show parity not in AC0. That is a technique by itself. You have also seen switching lemma and so on. So so if you are solving some problem in circuit complexity, you may use this, you may end up using it directly, or you may have to modify uh, the proof, or just take inspiration from it. Um, yeah, I don't know if that answers your question though.
Yes, thank you so very much. And would you like to recommend one or two, courses which, which are subsequent to this course and which can be taken in the next semester? Or, or can you suggest some areas wherein the courses are available online for everybody?
Hmm. Okay, so I think two very okay, I'll tell you a couple of things that follow this. So you saw boolean circuits, right? So this is sorry, what just happened? Okay, so this is one whole area in itself. You can look for the standard. I ran out, sorry, ran out of charge. One second. So, one standard, if you want to further look into this, one standard reference for this is a book by Yukna. This is the most standard book that is there, and there is a natural extension to this. Okay, so here you have Boolean circuits where you said that you are allowed and or negation gates, and I mean this is a complete base. This is one possible. Now you could ask further, what if instead of and or negation gates, allow, so these are boolean operations, right? So you take two boolean values, these are the operations you can do on it. Let's say instead of boolean values you are allowed to have numbers over integers, or let's say some field. Then what are the operations you can do? You can do all arithmetic operations. You can do addition, you can do multiplication, subtraction, division. So typical model is it's the same as the circuit that you had earlier. It's a DAG, but now the inputs, instead of boolean, this could be coming from a field. This could be integers, for example, and the gates that are there are, let's say, plus and multiplication. So these circuits are called arithmetic circuits, and this is one area on its own. uh, I think Nitin Saxena has a course on this, um, on Swayam itself. If okay, I'm not entirely sure. Okay, but I'll send you a list as an email. Okay, so this is one natural extension of Boolean circuits, and this is like one whole area of research. And yeah, next would be um, so Fourier analysis of Boolean functions. That is another. Um, yeah, that is another interesting topic, and you can find lectures by online lectures on YouTube by Ryan O'Donnell. And yeah, so this is basically, like I told you, like an area. It will give you techniques, a lot of techniques and a lot of results which you can use to solve problems of your, I mean, problems of your interest. And um, and coding theory is another very interesting area. This also has connections to pseudo randomness, cryptography, and so on. But yeah, um, I think there are lectures, online lectures of this as well. But a standard textbook for this is Salil, a book by Salil Vadan, and mm yeah. Okay, so these are, I mean, there are many more, but I think these are three next natural, um, I mean, natural extensions of it. But you don't need to, I mean, as such, if you want to solve, I think you have enough tools as such. But if you are interested, these are these are three nice extensions of that. Um,
And something at the intersection of the complexity theory and information theory, because I'm very much interested in this information theoretic part.
mm,
Probably people might be using this coding theory stuff, I guess, because coding theory, I mean,
hmm,
sometimes is related to the information theory,
hmm,
and in fact, information and coding theory is being taught simultaneously in a single subject.
hmm.
But then definitely I will look into these sources, and I would be grateful if you can send the list of the natural extensions to this course, yeah, through emails and the courses that we will. Thank you so very much, and thanks for making so much effort. I mean, in these 12 weeks, and I learned a lot from your sessions. And for me, it's like a one complete course. And you made Herculean effort in explaining that. Yes, thank you so very much.
Thank you. Okay, one second. I'll just stop the recording.